the recording too, because I know Rostin likes to watch it. There it is. There we go. Okay, there it is. So there's my region. I know mine's not the greatest drawing. You might have a better drawing than me, but I just want to make sure that you didn't stew too much about the boundaries. So those are the boundary conditions, or the descriptions of the boundaries. Should be relatively easy to deal with. Just, I mean, I tried to keep them nice and simple for things like this. So it'll take a few minutes, hopefully not too long, to do this, and then we'll see how we did. Oh, and I don't want to see any second derivatives, just so you know. If you were tempted, don't do it. No second derivatives for this. And hopefully you're coming down the home stretch here. Shouldn't be too many points if you've got more than 8 or 9. There are less than 8 or 9. Oops. Let's see, how many did I'll even tell you how many I got. 1, 2, 3, 4, 5, 6, 7. I got 7 or 8, depending on how you look at it. Try to wrap things up if you aren't. Thank you so much. Evaluate those points as best you can. Almost. There we go. Good job. All right, got some points. Got some evaluation. You got a chart. Show the chart to your little brother or sister. Very nice. Thank you. Excellent. All right. I think I got them all. Yeah, so it's hard. I think what's hard about this sort of thing is not that it's hard. It's just there are lots of steps. And so you know that if you get one step wrong, if you leave out a plus or a minus in your derivative, the whole thing is lost. Well, maybe not the whole thing, but a good portion of it. So let me show you what I got, and then we can, here we go, we can talk about it if need be. So here's my answer. Okay, so first things first, I did my derivatives. I was looking for my critical points in the region. So derivative in the x direction was negative 4x plus 4. Set that equal to 0, I got x equals 1. And then I got 3y squared minus 3 for the derivative in the y direction. That gave me plus or minus 1. So just note, I think I did my derivatives correctly, but like I said, you get one thing wrong. If I leave out a negative, it's going to blow the rest of the problem. But anyway, so this gave me actually 2 points. So you had the this x equals 1, y equals 1, and x equals 1, y equals negative 1. When I went to sketch these, the x equals 1, y equals negative 1 ended up outside the region. Here's the x equals 1, y equals 1. It's on the boundary, but it qualifies. So far so good? Hopefully. Okay, now we have the 3 boundaries to deal with, but I was kind, I thought. The only one that was at all a problem, and it wasn't that much of a problem, was y equals x. So let's deal with that. When you plug y equals x, change all of these to x's, well, just 2 of them. Then what you end up with is this function here. I simplified it. I hope I simplified it correctly. So there's the function after changing all the y's to x's, simplified, did the derivative, set it equal to 0. That one factored relatively nicely. Oh, it factored relatively nicely if I did it. No, I did it correctly. Whew. Got worried that I factored incorrectly. I got the factors right, didn't I? You can foil that, and you find that that's correct. X equals 1 and x equals 1/3. And because this is all under the auspices of this, then the y value will be the same as the x value. Those are my critical points on that boundary. Let me sketch them up here. 1/3, 1/3 is right there. 1, 1 is the same as, well, that critical point that we found already. Now let's do the other 2. These were a lot easier. So y equals 0 apparently I did first. It's a little bit messy here. This should be x squared. So that's f of x comma 0. I changed the y to 0. Did the derivative, set the derivative equal to 0, solved. And so since that was under the y equals 0 category, I knew that y had equals 0. So that's 1, 0 right there. And then for the x equals 3, similar deal. I'm going to change x to 3. So notice that the x's turned into 3's. So, did the derivative of that. And then set equal to 0, solved, got y equals plus or minus 1. As before, the y equals negative 1. We're not going to include. Oh, hold. Whoops. Someone should have yelled at me. Oh. Yeah. That better? Sorry about that one. Yeah, this one. This one is actually down there. Well, sorry about that. If that confused you from the get-go, you got to let me know, because I am as prone to error as, well, maybe not as prone, but I am prone to error. More so in my old age, I found it gets worse. Okay, so there's my one critical point on that boundary. It's right here, over 3 up 1. So you'll see that with the corner points, there's a total of 7 points. That one that I circled there is sort of, it gets, I've got it twice in my list, but only for, so I could be complete in my list. And then I just have to compute the function value. Here again, I did these in my head. So if I got one of them wrong, it's okay. I think I got the important ones correct. So I think this one might be, I don't know, because dealing with those thirds was a bit of a deal. You don't think it's right? But it's small. Here, I'll do this. Just a minute. There. That's the correct number. You just have to use your imagination. But it's not a max or a min. And then I got those as my max and min. But once again, I'd be happy. I'm pretty sure that the 1/3 isn't going to be either. So seems like there were some people had those. See that's okay. So some people had something different. Some people had those. I guess I can double check my math. What's the deal? Oh, the critical point on the boundary. That's it. A lot of you chose to use the corner point for the minimum. Like you didn't do the critical point on the boundary. This is a boundary critical point. So yeah, it's there. So here's where the minimum is, and the maximum is at that corner, was it? Yeah. So there they are. All right, questions about this? It's hard. This can take some practice. We're going to have to do more of these before next Friday so that you can do it well on the actual test. So I'll bring some, maybe not tomorrow, because tomorrow's going to be a problem with this. So there we go. So let's switch gears to this. So notice what this is asking. It's asking you to find a point on a plane that is closest to another point. Interesting. The language sounds like something that we are doing now. It's like optimization, right? It's the same as finding a maximum or a minimum. Here, we're finding a maximum. So the hardest thing about these problems, I don't know if you remember this from Calc 1 or if you've tried to block it from your memory, but I think the hardest thing that I had when I was learning this was coming up with the formula, coming up with the equation given the words, right? Coming up with the equation. So what I found was I was looking for, at least to help me, is I always looked for a superlative. Do you know what a superlative is? This is something that in high school they sometimes do. They vote on senior superlatives. Do they do this at Granville? No, they have you carry these brooms around instead. This is like the most likely to succeed. Anyone do that? Or the most likely to end up in a car wash? You did this? Were you the most likely to succeed?
I think one of mine was like most funny.
Okay, so most likely to be a security guard at a Eminem concert?
Talk themselves out of trouble.
Okay, very nice. Yeah, so this is like, yeah, so it's like the most, the biggest, the smallest, whatever it is. So those are superlatives. I look for a superlative in the body of the problem. And if it's an optimization problem, it will have a superlative of some sort. What is the superlative here? What is it that we're interested in? Which word is that? I can always pick someone, but I think you could just shout it out. Yeah, closest, right? Closest. It's usually going to have an EST, or in the case of those senior superlatives, it was always the most or the least, but they still have the ST at the end, don't they? So yeah, these are, we're looking for the closest. Just a minute. So let me go back here to the iPad for a minute. Closest. So when you hear the word closest, there is a mathematical formula for that sort of an idea. What's that? Yeah, distance formula. I didn't even have to pick a random person. So in that case, I'm interested in the distance formula. Distance formula. And you know and love the distance formula, don't you? This is going to be the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. So I need to find the smallest value for this distance formula. Yeah, what do you think? Okay, you can switch them around if you want, and it'll work the same because you're squaring it. Yeah, you can jumble them up if you want, but yeah, since you're subtracting and squaring, you'll get the same answer. Yeah, you probably learned x2 minus x1 squared. This is my early morning. It's not that early though. It's almost 10.
Early.
Early enough. Darkness. The darkness is descending out there. Okay, so there's my distance. All right, let's go back to the problem at hand. Closest to the point. So we've got two things going on here. We have a plane, we have a point. You can imagine the situation. The plane might be this plane, this surface of this desk, or the surface of your desk. And then the point could be a point up here, the tip of this Apple Pencil. That's the point, that's the plane. What's closest? You could figure this out. You could actually figure this out using vectors, but we're not going to do that. We're going to use optimization, calculus, derivatives, and so forth. So what's the closest point? You know where it's going to be. It's going to be directly below it, right? But let's say this the table was sitting at a tilt. It would be harder to tell. So let's go back and forth here for a sec. X1, Y1, Z1, X2, Y2, Z2, plane, point. So which is which? So Lucas, let's deal with the 541. 541, what would you like that to correspond to in my distance formula? I can make it x1, y1, z1, right? Okay, we're going to do that. So we've got 5, 4, and 1. Okay, so we've already established this. 5, 4, 1. Next, we need to deal with x2, y2, z2. Haven, where are we going to get x2, y2, z2? The only other thing we got there, right? It's that plane. So what would you like me to call x2, for example? So you can pick a number. Yeah, let's not pick a number. Let's just name it. Like what up there? It's something up there. So you said you're going to use this, right?
Yeah, I was thinking like the X.
Oh, the coefficient.
Yeah.
Let's use the other part of this x here. That is, use the x. So let's say x2 is equal to just x. Is that all right? And then what's y2? Just y. Let's leave off the 2 for now. And then what about the z2? Yeah, it's just z. So this is a point. I know, it's kind of silly. It feels silly, but x2, y2, z2 is a point on that plane. So I'm going to write that down up here. x2, y2, z2 is a point on the plane, x, y, and z. And we're going to get to that equation, though. Haven is dying to change some numbers here, and we'll do that in a minute. And so that means that my distance is this, 5 minus x squared plus 4 minus y squared plus 1 minus z squared, where the x, y, and the z are the point on the plane, are a point on this plane here. It's like someone's driving I don't know, something. Go-kart. Okay. Almost there. So now let me just point out that I have my formula. I'm going to call this F because it's hard to think in terms of D for, I mean, D is distance, but F is, no, actually I changed my mind. We'll get F in a minute. That's distance. Sorry. Okay, now let me show you a little trick that we're going to do pretty frequently in here, and that is that if we want to find the minimum distance. So the minimum of this function. You know what? That radical is going to be painful, isn't it? I don't want to have to deal with the radical if I can help it. And here's the deal: is if I have the minimum of this, it will correspond to the minimum of this. Come on. Sorry, leaf blower man out there is really distracting me. No, it is a leaf blower. I see the leaves flowing across the window. Okay, anyway. Yeah, get right up to the window there, buddy. Okay. Sorry about this. Anyway, if we find the minimum value of this thing and then just do the square root, we'll have the minimum value of this. And this is going to be easier than this, hopefully. Hopefully? Does everyone agree with this, that this is okay? Oh, he just went by the window. I wanted to wave. Now he's in this panel of wall. Maybe if I stand right here. Blowing. Okay, so anyway, we've got the function there. So we want to minimize this. Now what we've been doing up till now is, yes, no idea, is we've been doing functions of two variables, like x and y. This has three variables. And so I don't like it that there's three variables. I would much prefer two variables, because you remember the drill. Do the derivative in the x direction, do the derivative in the y direction, set them equal to 0. Let's do that. Oh, wait, let's get rid of the z. I thought he was done. Okay. So the way we're going to get rid of the z is we're going to do what Haven wanted to do up here, and that is, let's deal with this, use those coefficients of x, y, and z. And so here, what I'm going to do is I'm going to solve for z. Give me a second. I'm going to write this down. So 3z is equal to 6 minus x minus 2y. Is that what we're getting? Just make sure I got that right. So 3z is equal to 6 minus x minus 2y, which means z is equal to 2 minus 1/3 x minus 2/3 y. So I'm going to shove that up here into f, and now I've got a function 5 minus x squared plus 4 minus y squared plus 1 minus 2 minus 1/3 x minus 2/3 y. Whew. Okay, so let's back off for a sec, because I know some of you are completely lost. Oh, no, I don't think that. I think that there's probably a couple of you who are like, wait, where did that 1/3 come from? Which we can back up and try to figure out. So let's just back off for just a minute and recap. I'll give you a second to digest. Now, I don't know about you, but we're in familiar territory in the sense that back in Calculus 1, I can remember doing optimization where you were supposed to find the maximum value, like let's say it was the maximum height of something, the maximum height. But by the time you got done, the height was kind of like obscured by all the formulas in the algebra that you did, and then you optimized this other function. Yeah, that's not even a good example. Maybe you would do I know, it was things like boxes. Do you remember doing volumes of boxes and with different constraints? So you'd have the volume, but then it would change because you would have to get rid of extra variables. Anyway, this same thing goes here, is you're given this thing that we know the distance formula, that's recognizable, but then we have this additional constraint. The constraint is the plane. And after substituting and doing a little bit of algebra, that's what we end up with. Oh, squared. And that doesn't look at all like, well, it does sort of look like a distance formula of sorts, but this is the way it's going to be. You're going to get to the place where you're going to do your optimization and you're going to be like, hey, that doesn't look at all like what I'd started with, but that's okay. You've done your algebra correctly and you've done your substitutions correctly. You always want to end up with two variables. Here's my two variables, x and y, so that you can do your derivatives. And I would suggest in this case to do a little bit of simplification, but not too much. I would stop there. I know there's a temptation to square those binomials, but if you square the binomials, you're going to have to square that trinomial at the end. I don't even want to think about that. So I'm going to leave that alone and just go from here and do my derivatives. Okay, so I just want to show you how far afield we've gotten. Can you see that this problem and that look so different? Well, maybe they don't look so different to you, but to me. So when you get to this stage, if it looks like you're doing a different problem altogether, it's okay. And another thing I want to point out is you shouldn't expect to be able to go from this to this in your head. I can't do that. You gotta write things down and go through the trouble of saying, okay, I want to optimize distance, and then let's see what the distance formula is. Let's plug in the point. So notice that's the next thing I did. And then I was like, okay, I'm trying to find the distance between that point and some generic point, x, y, z. But I have a constraint on my x, y, and z, specifically the plane. And so I'm going to make that substitution in z. And then I've got this, and I simplified it a little bit, and that's what I end up with. By the way, oh no, we'll save this for the end. Okay, so next thing, let's do our derivatives. You know the drill here. This isn't hard. F sub x, f sub y. We're going to set each of those equal to 0. Once we get f sub x, you're going to be fine with f sub y. I know Roston could do this, but he's not here. Sarah, you get to do it for Roston. I appreciate your willingness. What's the derivative in the x direction of this thing? Beautiful. So if you're wondering where all this came from, Sarah used, in an expert fashion, used the chain rule. So let's just talk you through this though, just to be sure. So dealing with this first, multiply by 2, that's where the 2 came from. Leave this alone, first power, but then multiply by the derivative of this, which is where the negative came from. So that's the first one. The second one, same deal, multiply by 2. Oh, this one has no x's in it, so its derivative is 0. So we ignore that. Here, multiply by 2. That's where this 2 came from. Then you make the exponent 1. And then multiply by, do the derivative, which in this case is just 1/3. So that's where the third came from. All right, let's see if we can do the same thing with the f sub y. Sydney, do you have the f sub y, or can you talk me through this?
Negative 2 times 4 minus 1 plus.
It's okay if you want to just do it stepwise instead of all at once.
Plus 3.
What's that?
Plus 3.
No, it's just, yeah, multiply by the 2, so do 2. And then what's the exponent going to be? So this will be to the first power. And then do the derivative of what's in here. What's the derivative? 2/3, yeah. Yeah, so yeah, don't be afraid to, it's fine to just sort of talk us through it so that we see. So that's sort of the typical way that people will write down the derivative. And then we can clean it up and make it look pretty. Let me go ahead and do that. So it's 4/3. -1 plus 1/3 plus 2x plus 2/3. All right, well, I see some algebra in my future, but it's not hard algebra. This is two linear equations. They just have these thirds in them. Let me clean this up a little bit. Just give me a sec here. I'm going to write the f sub x over here, and I'll write f sub y over here. So give me a minute. You could do this yourselves. Okay. 4/9. Sorry. Apparently, you could do it yourselves probably better than what I'm doing here. Okay, I think I cleaned up the f sub x. You can double check my math. There, I think I got the f sub y. But once again, double check. I'll give you a minute to digest that. Oh, this switched. Sorry. I was looking ahead at the next. 10 minutes is one problem taking half an hour. That's typical though. I mean, especially as you're learning about it, we're taking our time. And okay, now the algebra. The algebra I'm going to breeze through a little bit quicker because I think that you can do the algebra. And I don't like fractions. I don't know about you. I hate fractions, so I'm going to multiply everything by 9 to get rid of all the fractions. So I've got -90 plus 18x minus 6 plus 2x plus 4y. Clean this up a little bit, and I get 20x plus 4y is equal to 96. Okay, on the left side here, I'm going to do the same thing, multiply everything by 9. 72, 18y minus 12 plus 4x plus 8. And then clean things up a little bit. It's going to be 26y 4x is equal to 82 and 84. So you can double check my math if you'd like. Looks like I could divide both of these by 2. Wait, that one will divide by 4. Okay, let me do that. 5x on the left, 5x plus y is equal to 24. And then on the right, sadly, did I do my math correctly? 18 and 8. Yeah. Okay, so this divides by 2. 42. So that'll simplify things because I could do this. Y equals 24 minus 5x. Stick that over here. Okay, 13 times 5, 65. So 65 minus 2, so negative 63x is 42 minus 13 times 24. It's 52 times 6, 312. I better do this on a calculator. No, someone with a calculator. Do 13 times 24. Tell me if I'm right. Oh, I got it right. Amazing. And then I'm going to subtract, which gives me 270 negative. Ooh, this is nice. So x is negative 270 over negative 63. Cancel the negatives, cancel 9, and you're left with 30 over 7. Okay, not that nice, but it's a number. Okay, so now we just have to figure out y, but we're going to use this here. So y is equal to 24 minus 5 times 37, whatever that is. I'm just going to box those up for now.